Hello and good morning, everyone. Good afternoon, wherever you're located. Thanks for joining this webinar. Let's just give it a minute to allow folks to join. I see participants coming online. Thank you. Get started in just a few seconds. Okay, we're a little bit past the top of the hour, so let's get started. Thank you for joining our webinar where we're presenting today on VT14, the tool for estimating organic carbon stocks using digital soil mapping. So let's dive in. Next slide, please. Okay, so I'm going to start off with some housekeeping items. My name is Stefan Jurka, and I'll be joined by my colleague Carolina Lisboa from Verra today on this webinar. We're also going to hear from Jim Kellner from Perennial. This is the organization that was the lead developer of VT14. We're going to present for about 40 minutes, give you some introduction to Verra, to the history of this tool, and then some key details of the tool. Then we're aiming to save around 20 minutes for questions and answers. Everybody should see a Q&A button at the bottom of the Zoom box where you can submit your written questions. We have disabled the live chat, but Q&A is your way to send your questions. We'll be able to respond to some of those in writing throughout the webinar, but we'll also respond to some during the Q&A live. However, there's a large audience joining this webinar today, so it's likely that we won't be able to answer all of the questions live or in writing. So please do submit or email us your questions afterwards if we didn't get to them during the webinar. And lastly, the webinar will be recorded and made available on Verra's website and YouTube channel afterwards. Okay, so those are the housekeeping items. Let's go to the next slide. In terms of an agenda, I will give you an introduction to Verra, overview of what we're doing, then hand it over to Carolina for the development history and applicability of VT14 in agricultural land management methodologies. And then Jim will present the details of the tool itself and the key components. And again, we'll have about 20 minutes for Q&A. Next slide. All right. Great. So many of you will be familiar with Verra, but just want to spend a minute for those of you that aren't to share what Verra does. So we are a nonprofit that sets the world's leading standards for climate action and sustainable development. On this screen, you can see the logos of the various programs we are operating. The Verified Carbon Standard Program, VCS program, is our flagship program. That's where the VT14 tool is operational. But we do run these other programs here that do deliver climate and sustainable development action. And we're very proud of that at Verra. Next slide. Great. So specifically on the VCS program, this is the world's leading greenhouse gas crediting program in terms of annual volume of issuance of carbon credits, which provide long-term finance to projects that are reducing or removing greenhouse gas emissions. To date, we have about 2,300 projects registered in over 132 countries and have issued over 1.3 billion carbon credits. So that's a large number, but in terms of what the atmosphere needs to seem to really reduce climate change and mitigate emissions, we need a lot more action. And so we're excited that VT14 is now part of the arsenal of options that project developers can use to achieve even greater climate ambition. Next slide. Great, just high-level point on VT14, and then I'll hand it over to Carolina. So this tool was published in August 2025, and we believe it will facilitate the robust and verifiable quantification of greenhouse gas emission reductions and CO2 removals, specifically in agricultural land management projects. And the tool is really based on robust and credible and up-to-date science and novel technologies that are coming online, and will enable and facilitate and scale up the rollout of agricultural land management projects to generate high-integrity carbon credits. So with that high-level introduction, I will pass it over to Carolina to provide some more details. Thank you.
Next slide, please. Thank you, Stefan. Hello, everyone, and welcome to the webinar. I will be walking you through the development history of VT14. As Stefan already mentioned, we just launched this tool in August 2025. This tool was a 30-part development lab. It was developed by Perennial Climate Inc. with the support of Terra Carbon. And the tool went through a public consultation period early this year, which lasts more or less 45 days. And during this time, we received nearly 200 comments with valuable feedback from stakeholders across the carbon and agricultural sectors. Following the consultation period, the tool went through a limited scope VVB assessment, and also an independent expert assessment, which was carried out to confirm that the tool was scientifically and technically robust. For everyone who is interested to see the announcements related to the VT14, you can find all the links to access all the reports, the communications, and any support material on the Verra website under the tool webpage. Additionally, you can also find Verra's YouTube channel. There is several resources that can be helpful to understand the tool itself, and as well as how the program works, and also the methodologies which are applicable with the tool. Next slide, please. Thank you. One thing it's important to mention, particularly to this tool, we ask the developer in the early stage, actually during the draft development, to establish an independent expert working group to support the development of the tool. This group essentially were established to challenge the developer and to try also to bring different perspectives from people who work on the market to make the tool more accessible to different contexts and scenarios and project needs. You can see here, this working group has two subgroups today. Yeah, one was the core group, which was more focused in science. And you can see here the list of the names of these scientists who helped and challenged the Perennial during the development. Dan Kenny, with work now for Med Agriculture. Jacqueline was former Terra Carbon. Brian McConken from Viresco. Sassan from NASA Jet Propulsory Laboratory. John Sandeman from Woodwell Climate. Alessandro Padux from INRI, and I joined only as an observer. And we have also another group which we call advisory group, which was more than 20 stakeholder representatives, being one from the VVB stakeholder group, but there were also project proponents and MRV providers and a few other scientists, which also where we request direct input from them in specific topics of the tool. Next slide, please. Yeah, to understand where the tool fits, it's helpful to have a look at the broad agricultural land management, or ALM, as we call, within Verra. It sets on the scope 3, sectorial scope 14, AFOLU. And you can see here to the right, the numbers of projects that we have on the Verra registers today, listed with one of the two methodologies that you can now apply the VT14. It's about more than 300 ALM projects in the Verra registry, more than 200 projects listed on the pipeline under VM42. And we have already 9 projects registered, officially registered. And for VM32, we have more than 15 projects listed in the pipeline. And so far, there is 1 project registered. What these methodologies have in common is that they focus on the quantification of soil organic carbon stock chains, focusing implementation of management practices in the field to increase soil organic carbon stocks. Next slide, please. So, as I briefly mentioned in the beginning, Jim will explain more in detail later, the VT14 applies to 2 ALM methodologies at the moment. It's at this moment, the VT14, it's only gonna be applicable to VM42 version 2.1. And to allow the use of the remote sense in this version of the methodology VM42, we launched on October 10th a correction and clarifications to allow specifically the use of remote sense when you're using this version, because as you know, this version of VM42 originally didn't allow the use of remote sense. But now any project listed or registered under VM42 2.1 can start to use if they want to. The next slide, please. And another correction clarification is going to be issued today to allow the use of VT14 under the measure approach only for VM32, which is the methodology for adoption of sustainable grassland through adjustment of fire and grazing, the version 1.0. And yes, it's gonna, the correction clarification document gonna be also available in the VM32 webpage. I didn't mention before, but it's also available in the VM42 webpage. It's there already, because it was launched a few days ago. And for both methodology, what I want to say is that they are, as you know, they are both going under a major revision. And the idea is that the next version of both methodologies will allow the adoption without any need for issue any correction clarification documentation. Next slide. Yeah, now I'm going to hand over to Jim. Thank you, everyone. Jim.
Thank you very much, Carolina. What I'd like to do here over the next 20 minutes or so is give you an understanding of the technical aspects of VT14, why the tool was developed in the way that it was, and then also provide some insight into the basic problem that we see VC14 existing to solve. At a very high level, the tool exists to solve the problem of quantification in situations where the previously existing approaches maybe weren't effective or weren't amenable to a particular solution in a particular part of the world. What the tool does is provide a way to bring digital soil mapping, a technology that's been around for several decades, that's the result, has thousands of peer-reviewed academic publications on all continents, bring this technology into compliance with the rules required in a VCS carbon program. And it does this in a way that is agnostic to the methodology. So we heard Carolina say, for example, that the tool can work under VM42 or other VCS methodologies, and it's also agnostic to the quantification approach. You can go to the next slide. One way to think about this is to recognize that if you, for example, are using a biogeochemical simulation model right now under, say, quantification approach 1, that might be a perfectly acceptable solution. The goal of VT14 is to provide a way to continue to do that in a way that reduces uncertainty, reduces some of the logistical burden, and does so without compromising rigor. That's what we believe digital soil mapping brings. It also provides the opportunity to use digital soil mapping as a direct quantification approach. So something close to quantification approach 2, for example, in VM42. As a tool, VT14 works across ALM methodologies. It's agnostic to the methodologies. And we say that it unlocks compatibility between models because it can be used, for example, as a primary measurement source under quantification approach 2. It can also be used as an input into quantification approach 1 approach under, say, VM42. Digital soil mapping can work in place of physical soil samples. A good rule of thumb and way to think about it is any place where you can imagine using physical soil samples to get a direct measurement of soil organic carbon, VT14 can provide an estimate of soil organic carbon stock that is like that and can be used in place of that. You can go to the next slide now. Let's talk briefly about what digital soil mapping is. At a simple level, what it is a statistical technique, and it works like regression, where you have inputs and outputs. The inputs are things that we think are related to soil organic carbon stocks. So, for example, the inputs could be measurement of climate, weather, topography, soil type, topographic slope, like which direction the landscape is facing and how steep it is, for example. And also measurements from remote sensing. There could be things in there about the greenness of the landscape over time, the dates of harvest or planting. There could be information in there about practice, like cover crop or tillage status, or really anything else that you think might be related to or predictive of the amount of carbon stock in the soil. Those are the inputs. And in this way, you can think about digital soil mapping as working kind of like a biogeochemical model. The difference is that a biogeochemical simulation model works on the basis of physical, chemical, and biological knowledge, whereas digital soil mapping tries to solve the same problem, but does so using statistics. The output of a digital soil mapping model is a prediction. It's a prediction of the amount of soil organic carbon or bulk density or soil organic carbon stock at a given location. The way you can imagine building a model would be like this. You go out into the real world and imagine you collect a bunch of soil cores at a bunch of locations. And at each location, you have a latitude and longitude, so you know where the core came from. And then you send the soil core off to the lab and you get back a number. And that number is typically soil organic carbon as a percentage by mass. You would then link that number with the independent variables I described, topography, weather, tillage status, and so on. And you'd have a gigantic table. And that table would represent rows, each of which is a unique soil organic carbon measurement, and columns, those are the input variables. You then use a statistical model to learn the relationship between those inputs and the outputs. Once you have that relationship, the value of it is that you can use that relationship everywhere to make a map of soil organic carbon. And importantly, you can use that relationship to make a map anywhere, even in the places where you don't actually have the measurements. The way to think about this is that what the model does is fill in the places between the measurements. This is a very standard approach in the field of remote sensing. It's used for mapping soil carbon, for example, from space, and many other properties. You can go to the next slide now. The benefits of digital soil mapping, we believe, are these four. It reduces sampling burdens. It reduces costs because it reduces sampling burdens. It reduces uncertainty, that's a statistical advantage, and it's more scalable. I'll tell you what I mean by each one of these. The reason why digital soil mapping reduces sampling and reduces cost is because you can get more out of the samples by way of a digital soil mapping model than if you just directly use the samples alone. So one way to think about this would be to ask, how much uncertainty would I have if I use samples alone? Imagine you went out and collected, say, 250 samples in a location. There'd be some amount of uncertainty in your estimate of the mean SOC stock as a result of those samples. Versus you can use a digital soil mapping model. So you take those 250 samples, use them to train a digital soil mapping model, use it to make a map, and then calculate the mean and the uncertainty from the map. What I'm saying is that what we find is that you can get to smaller uncertainty with the same number of samples by way of digital soil mapping. Therefore, it reduces the sampling burden and reduces the cost by reducing the number of samples. Because digital soil mapping is a comprehensive map that has many thousands to tens of thousands, hundreds of thousands, sometimes millions of individual pixels in it, it reduces uncertainty because you're estimating the mean and the uncertainty in that mean using much more information than would be feasible to do using just samples alone. Digital soil mapping is arguably more scalable. It's scalable because it works anywhere. Digital soil mapping doesn't depend on a pre-validation at a different location that you then use to justify its use in your project. So for example, you wouldn't say that a digital soil mapping model that works in California is therefore going to be able to be used in Kansas. Instead, you would simply validate the digital soil mapping model in Kansas or wherever your project is. What this means is that you can always build a local digital soil mapping model, and the history of academic peer review shows that that has been done hundreds of times all over the world in a very wide range of systems. You can go to the next slide now. I'd like to describe two use cases for digital soil mapping, and I'm going to use the language here of VM42, which has quantification approach 1 and quantification approach 2. Quantification approach 1 is called measure and model. It's where a biogeochemical simulation model is used to forecast the change in organic carbon stocks. Under the tool, you could use VT14 to support the use of a biogeochemical model under quantification approach 1. What you would do is, instead of using direct physical measurements of SOC to initialize the biogeochemical simulation model, you would use the output from digital soil mapping as your input source. The benefits to doing so, we believe, would be that you're going to have a more precise estimate that is being used to initialize the biogeochemical model and able to get there at a lower cost. The same validation requirements apply under quantification approach 1 when VT14 is used as when it isn't used. It's important for me to say that VT14 follows the target methodology. So if the target methodology has rules about the timing or frequency of validation, those same rules about timing and frequency of validation would apply whether or not VT14 is used. You can go to the next slide, please. Quantification approach 2 in VM42 is direct measurement. The traditional way that this would be done would be to go out into the field and collect direct physical measurements of SOC stock at a given point in time, to come back later, repeat those measurements, and then compute the change in SOC stock by simply differencing the means. Here, that same thing is possible, but instead of using physical soil samples to calculate the difference, we would use digital soil mapping. So we would use a digital soil map to calculate the mean SOC stock at the first point in time, get its uncertainty. We would do the same thing at the second point in time, get the uncertainty, calculate the difference between the two. Now it's the difference between two digital soil maps, and then integrate the uncertainty to get a comprehensive estimate of the variance of the change in SOC stock. The variance of that change is the basis on which the uncertainty deduction is calculated. There's a worked example of this provided in an appendix to VT14. You can go to the next slide now. I'm going to try to walk through here some of the details of how VT14 is actually implemented. And what we're going to do is we're going to take this particular diagram and they're going to walk through the diagram in 3 components. So before we go to the next slide, I'll say that what this diagram is showing you is a complete overview of the process of actually implementing the tool, the nuts and bolts of how to go about building a digital soil mapping model from one end to the other, going all the way to the uncertainty deduction at the end. Let's start at the top by going to the next slide. What we see here is the initial steps of model calibration and validation. So if we start here at the box labeled number 1 on the left, you can imagine a project area. It's represented by those green boxes on the left, and those dots represent physical soil sample locations. These are the locations, like I described to you previously, where we've measured SOC as a percentage by mass out in the field, and we have a latitude and a longitude for each one of those points. We also associate that with a set of independent variables. Those are things like temperature, precipitation, soil type, topography, management, practice data, and so on. And that's labeled here in under number 1 in the table that I described to you earlier called covariates. Then what you do is you build a model. Now the tool is open to how you do this. You can have an independent calibration set and an independent test set. The calibration set is what you use to build the model. The test set is what you use to validate it. It's how you know that the model is actually working. The tool provides a wide range of ways you can do this. One way is independent, so the training set or calibration set and the test set, they never have any overlap. But an alternative is called cross-validation, which is what we expect most people would do. Cross-validation involves taking all of the data and then randomly removing a subset of it, calibrating the model on one part of the data, and then testing it or validating it on the other part, the part that wasn't used for calibration. You could imagine that you repeat that process many times so that you have a large and comprehensive set of test predictions on every observation in your data set, but the test prediction came from an instance of the model where the test observation was not used for calibration. So you're maintaining the separation between calibration or training and validation or testing. That's called cross-validation, and the tool permits that. The number of steps in that cross-validation process is indicated here by the letter K. So you would go through that process many times, and you would then generate predictions, and you would generate a prediction interval, which is an uncertainty estimate. So for example, a given point that we measured might have a true value of SOC as a percentage by mass of 1.2, and we might predict 1.15. And there might be an uncertainty range around that, and the uncertainty range might go from, say, 0.9 to 1.4, just as an example. And that range is represented by that distribution there under number 4. When we put all of this data together, we get to box 5 over there, which is a set of true measurements, the observations, and then the associated predictions, what the model believes the value should be given the calibrated version of it. And then we have a 90% interval, the uncertainty range for every single prediction. You can go to the next slide now. At this point, the model has to pass 3 tests. We think of these tests as guardrails and safeguards that ensure that the model is rigorous. The 3 are a coverage test, what we call an R-squared test, or an amount of variance explained test, and then a bias test. The coverage test looks at the 90% interval, and it says that the true value of that model, of that observation, needs to fall within the 90% interval at least 90% of the time. If that's true, then what that tells us is that the model's uncertainty is properly estimated, and one can have confidence using that particular model. The model also has to pass an R-squared test. What we're saying here is that the R-squared of the model has to be greater than 0. When many people hear this for the first time, they think that sounds like an incredibly low standard. And let me tell you that in typical situations, the R-squared will be much greater than 0 and will need to be much greater than 0 for the project to produce credits without losing all of them to an enormous uncertainty deduction. The justification for 0 is that it's objective, and it means that the model is providing a better answer than using samples alone. The third test is a bias test. And what we require here is a t-test on the model residuals. What we want to see is that the model residuals, that is to say the difference between the observed value and the predicted value at the sample level, is not different from 0. When that's true, what that means is that the model has some error in it, but the model neither overpredicts nor underpredicts on average. You can go to the next slide now. If the model passes those 3 tests, one then goes on to the process of inference. So you would take the model, you would use it to make a map of SOC stock at the project level, also in the baseline, if baseline control sites are being used, and then you have your map of SOC stock. There's a critical step here related to uncertainty. VT14 requires the use of geostatistical methods to get a good estimate of the variance of SOC stock. Geostatistical methods, that simply means that we are not making the assumption that the error in the model, in the map, is independent. We are looking at the degree to which model error is spatially correlated. One way to think about this is to imagine a prediction at a given location. Imagine that prediction is off. Let's say it's high by 0.1. Well, if you move 1 pixel to the right, the model's probably also high by 0.1 at that location, because locations that are close together probably have errors that are similar. The tool explicitly accounts for this using geostatistical methods developed in a paper published by Wadu and Hoovelink in 2023. It's cited in the tool. Requires you to estimate a variogram that's shown there in step 12. And what this ends with is an estimate of the variance of the mean. That gets you to a variance of the mean at a single point in time. The tool then describes in equations how to take the variances at 2 points in time, including their covariance, and get all the way to an estimate of the variance of the change in SOC stock. It is that variance that is then used to generate the uncertainty deduction under, say, VM42. You can go to the next slide now. This is a map showing you how we think about uncertainty deduction. I described that these methods rather are based on a paper published by Wadu and Hoovelink in 2023. This map is simply showing you a geostatistical simulation. So this is not real data, but it's designed to illustrate to you the concept of spatial structure in SOC stock and one of the reasons why we need to deal with the spatial component of the error. I'll just say here that there's an appendix published with VT14, it's Appendix 4, that has a worked example, including computer code, that shows how to implement all of the calculations in the tool, including the geostatistical methods, and getting all the way to a simulated example of an uncertainty deduction under VM42. When you do that, it looks like this. You can go to the next slide, please. These are 3 examples of an uncertainty deduction calculated for a simulated carbon project. This is what's in the appendix to VT14. So you have access to this code. You can reproduce this yourself, or you can just read about how we did it if you don't want to get into the code. And what this is showing you is the kinds of uncertainty deductions that would be expected under this one hypothetical project under a given set of conditions. So the important thing to emphasize here is that VT14 doesn't change the definition of the uncertainty deduction. It follows the uncertainty deduction definition of the target methodology, in this particular case, VM42. What it does is come up with a set of guidelines, a roadmap, so to speak, that explains how to get to this point using digital soil mapping in a rigorous way. You can go to the next slide, please. I'd like to conclude before handing it back to Carolina by saying that what we believe VT14 represents is a rigorous framework, a version 1, so to speak, to bring digital soil mapping into compliance with VCS carbon programs. It's applicable worldwide, anywhere that the methodology, say VM42 or VM32 can be applied, VT14 can be used. It has critical safeguards. It requires model validation, that is validation of the digital soil mapping model itself within the domain of the project area itself. It requires demonstration that the digital soil mapping model passes 3 tests: the coverage test, the R-squared test, and the bias test. And we see those as critical guardrails and safeguards that are designed to keep the tool on track and lead to conservative crediting. Finally, the tool brings novel and rigorous calculation and propagation of uncertainty all the way into the uncertainty deduction using geostatistical methods. Carolina, back to you.
Great. Excellent, Jim. Thank you so much for the very comprehensive presentation. I hope everybody has enjoyed it and learned a little bit more about how to use VT14. We know it's very complex, but we are here to help. If there is any questions about how to apply the tools, you are welcome to come back to us. But to proceed, so I just want to make some final remarks. I want to announce that we are today releasing a correction and clarification for VT14 because we found some errors in 2 equations there, equation 5 and 7. They are minimal errors, but they are very important and need to be fixed. I invited you to have a look at the website, the VT14 webpage later today, and you can see more details what these corrections are about. Next slide, please. The next announcement is that we're gonna be launch soon a call, open a call, actually not loud, but open a call to invite experts in DSM to become an independent model expert. As you know already, for VM42 and the module 53 also requires the independent model assessment, and that's gonna be the same for the VT14. It also will require an independent model assessment here. And yes, watch out for this call because we will need your expertise also to help us to assess how the project proponents are applying the use of the tool. And it's gonna be an open call, possibly starting within the next 2 weeks. And the list of the approved applicants gonna be available in the Verra website as well. So a last word about the tool. We want to say the VT14 is a Verra tool, which is publicly available to any qualified user, such as MRV providers or project proponents. And if you have any specific question, please reach out to the email we're gonna post in the slide later on. But I think now we can already move to the Q&A sections, and I'll hand over to Stefan.
Yeah, wonderful. Okay, thank you so much, Carolina and Jim, for that nice overview of VT14. So we have a nice chunk of time now to get into questions and responses. And please keep submitting your questions. We've answered a few in writing, but I think we'll try to answer as many as possible live. The first one I will pose for Carolina, and it's really a summary question. I see several questions related to the topic, but I'll try to summarize here. What happens in scenarios where there appears to be misalignment between soil sampling guidelines in VT14 and VM42?
Thank you, Stefan. Yes, we have been receiving these questions quite often already, and we understand that it's not so straightforward to combine both guidance, and this guidance should be seen as complementary guidance. The guidance for VM42, it doesn't override the guidance for VT14, and the other way around is also valid. The way to see that is like you look at the guidance for VT14 as the guidance to for requirements for soil data for calibration and validation. As for the VM42, that is guidance for soil sampling, which is really about the identification of the project area, minimum requirements in terms of soil depth, which should still be valid. And I don't see VT14 overwriting that. But if you have specific questions that you feel like this guidance is conflicting each other, please reach out to us that we can clarify the best way to read both guidance. Thanks, Stefan.
Yep, thanks, Carolina. Okay, a question for Jim. How does the use of digital soil mapping reduce the sampling required for VM42 quantification approach 2, which is measure and remeasure? Does it allow reducing the number of strata to be included in the stratified sampling?
Okay. So on the question about strata, I'm going to have to defer to Verra because that's really a question about methodology. And as we just heard from Carolina, in general, when there are questions about a methodology, the methodology is in charge. However, there are issues in VT14 that are updates that are unique to the use of digital soil mapping. For example, there's guidance in VT14 about the particular spatial distribution of samples that one uses, because you need a special kind of spatial distribution in order to be able to estimate a variogram properly. So in that case, VT14 is saying something that VM42 is silent about because it doesn't have that requirement in it. So on the issue of the strata, I'm going to say that's a Verra question. On the question about how does it reduce the sampling uncertainty, the way that I would put it is like this. Using a digital soil mapping model is allowing you to squeeze more value, so to speak, out of every sample because you are using a model, and then you are using the sample size that comes from the predicted model output, rather than using the sample size of the samples themselves. So probably many of you know or are familiar with the challenge that calculating a change in carbon stocks in agricultural land is a difficult problem. We're trying to detect a very small change, and often the error in the samples or the error in the sampled mean from physical soil samples is much larger than the change that is trying to be detected, which creates a real challenge. What that means is that one has to use an inordinately large number of physical soil samples in order to get the error in the mean to be small enough that the change becomes detectable. And sometimes the number of physical soil samples that would be required is so large that the project becomes either logistically or economically or both infeasible to do. So the reason why digital soil mapping reduces the sample number and provides an answer to that problem is because it doesn't try to use the samples alone. It's taking those samples, building the digital soil mapping model, generating the digital soil map, which might have tens of thousands, hundreds of thousands, potentially millions of individual pixels in it. And you can think of every one of those pixels as being kind of like a physical soil sample. It's not, of course, it's a modeled output, and it has more error in it. Each individual pixel has a little bit more error in it than an individual physical soil sample is, but they're very, very roughly speaking, they're the same kind of thing. So when you have tens of thousands, hundreds of thousands, millions of individual pixels, and then you aggregate them and you compute a mean, and you properly account for the geostatistical sources of error in that mean, what you end up with is a very precise estimate of the mean. That's the way you get to the sample reduction.
Thanks, Jim. That's great. Carolina, is there anything you want to add to that about the strata question, or should we move on?
Yes, I think it's best if we get this in written form, what's exactly the concern about the certification guidance, because like I said, I don't see them being conflicted. And also, as Jim just mentioned, the VM42, I think it's more about to understand about the must, the should, and the might. And the VM42, specifically for certification, if I remember correctly, it's not so prescriptive, but the tool is much more restrictive to that. It's really depend how you are using the guidance for the tool to do your sampling again. And the certification of a project, it's more a guidance of VM42 to help a project proponent to have a previous understanding or estimation of what about the variance of the population. And the tool is there to help you with an excellent, as an excellent tool to help you to have a better estimation how to get this data, this information, to then do your sampling, right? And yes, it's quite technical and complex, and it's really going to be specific about which specific topic or a specific way you want to use the tool or the guidance for VM42. And again, please reach out. We are more than happy to discuss with you and clarify the concerns.
Okay, wonderful. Thank you. Let's keep moving because there's quite a few questions rolling in. Here's one, I think probably for Carolina. I see quite a few projects registered under VM42 that used remote sensing prior to VT14. How is this possible, and how is VT14 new?
Yes, thank you for the question, Stefan. Yeah, specific to that, yes, that's true. There are some projects that use remote sensing. Just to correct, they use remote sensing, but not VT14, because VT14 was just launched now. But those projects, they were registering previous version of VM42. And the previous versions of VM42 did allow the use of remote sensing already. Only the version 2.1, which was very explicitly saying that it was not allowed. But again, now we made this possible to use remote sensing under the condition that meets the criteria of VT14 specifically. I
Yeah,
hope
thank
that
you.
clarifies.
Yeah, and I might just add a further point, which is that remote sensing for things like activity data, tillage detection, or cover cropping was already and continues to be allowed, right? What we're talking about here and looking at with the tool is remote sensing for soil organic carbon stock or content detection estimation. Great. Here's another question, probably for you, Jim. How does the tool and digital soil mapping, with its inherent spatial heterogeneity and significant uncertainty in measuring soil parameters, address this significant uncertainty now scaled across the entire model?
I think I understand the question. The key thing I'm wondering about is what's meant by significant uncertainty in soil parameters. So here's the answer. One of the things that is, I think, powerful about the way that the working group designed VT14 is they designed it to be outcome-based rather than input-based. What does that mean? Well, to be input-based is to say, here's a set of rules you have to follow, and if you follow the rules, that's good enough with no further checking. That would be input-based. That is not what VT14 says. VT14 is output-based, outcome-based. What that means is that VT14, you have to be able to prove that the model actually works. And if you cannot prove that the model works, it cannot be used. Those are the three safeguard tests that I described. In addition to this, let's imagine that somebody produces a low-quality digital soil mapping model, one that has significant uncertainty in it. What will happen to that person? Would they be able to issue credits that don't really exist? Well, we believe, the working group believes, that the way the tool is designed disincentivizes that behavior, because if you have a lot of uncertainty in the model, say that the model is badly biased, what will happen is that will show up in the model prediction error, and that will propagate through to the uncertainty deduction, and the project proponent will end up having to take an uncertainty deduction that could exceed more than 100% of the value of the credits. The tool was designed by the working group to bring about that kind of outcome, right? And this is what I mean when I say validation with safeguards. It's designed to be something that isn't amenable to getting away with or manipulation or gaming. It's designed to incentivize good behavior, because what we want is genuine credit claims.
Great, thank you, Jim. That was informative. A couple of, I think, straightforward questions for you, Carolina. I'll just read them both off. Does the project proponent need to use both VT14 and VMD53? That's the modeling module guidance that's used in conjunction with VM42. Do they need to use both, or is only one allowed? So that's the first question. And I'll just read the second one. Is there any possibility of using VT14 in REDD+ projects to measure soil organic carbon?
Yeah, thank you, Stefan. For the first question about the use of guidance for VT14 and the VMD53, the straight question is yes. you're gonna need to follow the guidance of VT14 to generate the input that you then you're gonna use to as input data to feed the biogeochemical model. Therefore, you need to follow the guidance for the biogeochemical model to then use the model biogeochemical models, right? VMV 53. Yes, again, that, like I said in the beginning, they're complementary guidance. They should not conflict, but if there is any point you feel like they conflict or it's confused, yeah, reach out to us. We can clarify that, the way to use the guidance. For the second question about if it's possible to use VT14 in VM007 Red Plus projects for measurements. At the moment, the tool it's only allowed for ALM methodologies, VM42, improved agricultural land management, and VM32, which is for grazing. But I want to say the tool was designed to estimate soil organic carbon in any situation. But that was designed that way because we hope that in the future we can do further alignments to allow the use of the VT14 in other methodologies, perhaps some which already existed, or future methodologies for the agricultural sector. But for now, the tool is only applicable for VM42 and VM32.
Okay, thanks for those clarifications. Great. Let's get to a few more, and also Jim or Carolina, please feel free. I think you have access to the Q&A box as well. If you see an important question to answer, feel free to jump in. I have one here that I can read out maybe for Jim, but I'll let you decide. Can VT14 be used for backcasting carbon stocks?
Okay, I think this is a dual answer. This is a Verra answer and a VT14 answer. So I'll take the digital soil mapping part of it, and then I will let Carolina speak to Verra compliance. The VT14, yes, let me stop. Digital soil mapping can be used to predict SOC stock in the past. The reason for that is because once you develop the mapping, the model, if you're willing to assume that that same model applies over time, which to be clear, VT14 requires continued demonstration of that fact going forward. But imagine for the moment that that had been demonstrated and we're in a scenario where we felt comfortable extrapolating, say, 1, 2, 3, 4 years into the past. There's absolutely no reason why digital soil mapping couldn't be used to do that. Now I'll let Carolina say whether that is allowed under a VCS carbon program.
Thank you, Jim. Yeah, depends. The answer is depends. If you are back modeling, using the tool to feed biogeochemical model to back model soil organic carbon stocks, depends why are you using that for? You can use that to do estimation of stocks in the historical look back period, or you can use that to make predictions, excellent estimations to help you to produce an initial soil map to guide the certification of your soil sampling. But to do estimations from time zero, let's say you want to do back model from time 3 years to 0, that's not allowed. You can only, then you are required to sample again, and then you can initialize your model. But you can only make predictions forward, but not backwards for crediting. I hope that clarifies the question.
Sure, that's great. Thanks to both of you. Cool. So we have about 5 minutes left. We're going to keep going, but I'll just share that we're getting some really great questions here. Realize now that there's no way we're going to get through all of them. So please follow up via email if you want a quick response to your question. We'll also be looking at these in the context of clarifications that we could be making to the tool. This is a version 1 of the tool. As with any Verra tool or methodology, we're using a continuous improvement mindset, and we'll be taking information, early lessons learned, and making updates as needed to the tool. And so this is a really helpful kind of initial stab at that, at these questions coming in. Okay, with that said, let's keep going just for a few more minutes. I have a question here for Carolina. Is Perennials the only accepted model, or can we use, for example, the Open Land Map Soil DB?
Thank you. Thank you for these questions. No, it's not only Perennial which can use a VT14. So in fact, in the section 5 of VT14, subsection 5.1, there is a clear guidance on the selection of models, and there is also a list there in the VT14, which are make suggestions for some models. Specific to this model you are asking, I will not know the response because I don't know this model, but any model which meets the criteria for VT14 are allowed to be used. Maybe Jim, you want to extend on that?
Yeah, I agree with everything Carolina said, and I'll tell you the working group designed this not thinking about this being approval of a model. So even today, I would say there is no model that is approved for VT14 because VT14 is not about saying this one thing is now usable. What it is a recipe. It's a set of instructions. Anybody can follow those instructions. So rather than saying, for example, this particular cake is the one that you're going to eat, instead, VT14 says, this is the recipe to make a cake. Now anybody can make a cake, and it can be any kind of cake as long as it follows that specific set of instructions in that recipe. That's how VT14 is set up. And we did that on purpose to encourage innovation. We want people to bring a wide range of backgrounds, experiences, skills, approaches. It could be machine learning, it could be Bayesian, it could be traditional statistics. There could be methodologies, that is to say, like statistical approaches that don't even exist today that somebody will use under VT14. And we wanted to come up with a set of guidelines that would encourage that kind of exploration and innovation.
Great, thanks both. Okay, we only have a couple minutes left. I'd like to ask either, is there any burning question that either of you have seen in the Q&A that you'd like to answer in a rapid fire way?
Maybe I'll let Jim start and then I can.
Okay.
There's so many burning questions.
Yes.
Well, there was one question about the use of DSM for biogeochemical model calibration, validation, and how that works. Is it specified? Is there a sample size requirement, or do you just iterate, or what? And I want to say that the answer is, to the person who asked that question, it's more like your iteration question. We did not specify exactly what sample sizes would be, and that was deliberate. And the reason for that is partly because nobody really knows, and it's likely to be highly context dependent. So if we had a sample size requirement, it's likely that it would be overkill in some situations and probably insufficient in other situations. So it's like the worst of both worlds. You're asking some people to do too much and others to not do enough. And so that's why the outcome-based approach to the validation of the DSM model is in there. How many samples do you need? You need enough to pass those tests and get to the point where you have a tolerable uncertainty deduction. People with experience in digital soil mapping would be able to give you advice about what that's going to look like in practice and get going down the road of developing a model that's going to be able to meet those tests and actually work in a real carbon program. And on the issue of validation of biogeochemical models, VT14 does state that you can use the digital soil mapping output as part of the true-up mechanism for a biogeochemical model under QA1. So the answer to that is yes.
Great.
Yeah. Yeah, for me, I don't have any specific one. I think many of them, they are like more or less about the same topic. But what I want to say is that first of all, I do appreciate all the questions. It's very welcome. And our team, we're gonna compile these questions, and our intent is to publish in the website FAQ section for VT14 with the hope to clarify any concerns or doubts about how to use VT14.
Wonderful.
Respect to.
Yep, that's great. Okay, well, we're a minute over time and we want to respect everyone's time. So again, thanks, Jim, Carolina, for this overview of VT14. We're super excited to see this tool now available for use and look forward to working with the community to see it applied in the real world. Thanks again, everyone. Have a great day.